Okay, so we're going to begin with the second chapter for week 2. And the chapter is about radiation fields. So it's basically a theory of radiation fields. And by radiation fields, I mean electric and magnetic fields. And I want to start off with first explaining why we need fields, because we can always work with particles, right? And we can just say, okay, we have a collection of charged particles here. They all apply some force on each other and they make each other move. So why don't we just go from first principles there and compute what the dynamics of this charge particle ensemble is? We don't need any fields in that case. That's strictly speaking true, but the problem becomes very complicated and intractable. And the reason for that is, let's say you want to look at this particle right here, where my pointer is. And I say, okay, I'm going to calculate the forces on this particle from all the other particles, and I know their positions, velocities. And then I'm going to solve for the dynamics of this particle. So the moment this particle moves because of the force, its effect on all the other particles is also changing because its position is changing, right? And the force depends on the distance between particles. And so you end up with kind of a chicken and egg kind of loop where it becomes highly complicated to solve for the dynamics, and in many cases becomes an intractable problem for all practical purposes. So to get around this problem, we kind of break the problem into the two parts. And I kind of like to think of it as a type 1 and a type 2 problem. So we kind of break this one problem into two separate problems. And a type 1 problem is where you try to compute the dynamics of a given particle. Okay, so in this case, let's say this particle, given the fields of all other particles. So what do I mean by fields? So fields are just fictional quantities, right? You just say that the effect of all the other particles are summed up in the form of an electric and a magnetic field, which is specified. And these fields apply forces on our test particle, and then the particle moves. So in the type 1 problem, we kind of say that the fields are known, okay? They're already provided, they're known a priori, and we only calculate the dynamics of our particle, which we are interested in. A type 2 problem is the converse of that. You say that I know the dynamics of all the particles, and I'm just going to calculate the fields given the dynamics, so the positions and velocities of all the other particles. So you kind of break the problem into two. Neither of them are going to give you the perfect solution, but in most cases of interest, they give you a solution that is good enough. So in many cases, you can sort of assume that you already know the electric and the magnetic fields and you're only solving for the dynamics of the particle. Or you can basically say that, okay, I'm going to calculate the electric and magnetic fields given that I already know the dynamics of the particle. In reality, of course, this type 1 and type 2 have to be iterated, because once you calculate the fields from the dynamics of the particles, which is a type 2 problem, those fields are going to apply forces on the particles and make them move. So, your base initial conditions have already changed in your type 2 problem. So there are some cases where we try to find a self-consistent solution where, both of them are solved together. But in all cases of interest, it's always useful to first work to kind of break down this problem into particles and fields. So particles being charged particles, their dynamics, and the fields being the electric and the magnetic fields. Okay, so let's look at what a typical type 1 problem looks like. And the only equation you really need to know to solve any problem of this kind is called the equation for the Lorentz force. So it's an equation that specifies the force acting on a given charge. And that force is directly proportional to the magnitude of the charge, Q, because the magnitude of the charge basically specifies how strongly a charge interacts with electric and magnetic fields. And then here is the force dependence on the electric and the magnetic field. So on the electric field, the force is always parallel to the electric field. So it's quite simple to work with the electric fields. The force is just the field times the charge. But it's a little more complicated with the magnetic field. The force from a magnetic field actually depends on the velocity of the charge. And the dependence is given in this cross product. So V is the velocity of the charge, C is the speed of light, V cross B, and B is the magnetic field, and that's the force. So the force is not parallel to the magnetic field. Actually, the force is perpendicular to the magnetic field and the velocity because of the nature of the cross product here. The other thing to notice here is this C in the denominator. If you're working with MKS system of units, then you don't have this C, but you know the value of B is going to be different in those units. We're going to be working with Gaussian units. And the reason for working with Gaussian units is as long as you're doing calculations in vacuum, Gaussian units are just simpler to work with because you don't have permeability, permittivity, all of those constants. And the other nice thing about Gaussian units is for a plane electromagnetic wave in vacuum, as you'll see, you'll actually show this later, the magnitude of E, so just the absolute value, the length of this vector E and the magnitude of B are the same. So you get a better intuition of which is the more important force. So for instance, if your particle is not relativistic, then V by C is going to be much, much smaller than 1. And so if you're talking about what is the force applied on a particle by a plane electromagnetic wave, where E and B have the same magnitude, you can basically disregard this term, right? Because it's just going to be much, much smaller than the term from the electric field itself. Okay, so yeah, so the main thing to keep in mind is, of course, that B only acts on moving charges. So if you have a charge that's not moving or moving extremely slowly, then the magnetic field doesn't have a big effect on the dynamics of the charge. Assuming, of course, that E and B are the same magnitude. Of course, you can have an external magnetic field where B is so much stronger than E of some electromagnetic wave that even though V by C is small, this term becomes important. And we'll solve some problems on cyclotron motion where you'll see that. Okay, that's for a single point charge. We can also talk about volume elements where we kind of treat the collection of charges as an ensemble or as a fluid. And you know, that's a very straight generalization. So I can define a charge density. That is just the density of charge. Okay, so delta V is a volume element. And as the volume element tends to 0, the average charge in that volume is the charge density. So it has units of charge per unit volume. Now we also have in the Lorentz force term, the second term, the magnetic force, and there the velocity is important. So corresponding to that, you can define a current density, J. And again, the current density is basically the average value of Q times V. Okay, so this Q times V is analogous to a current. So a charge with a velocity is a current. And its volume density is basically given by the current density. So just be aware that rho and J don't have the same dimensions because I multiplied by V here and there's no V there. So something to keep in mind when you check the dimensionality of equations when you derive something. Now I can basically write the Lorentz force like this. I can say what is the force per unit volume element. So this is the magnitude of the force per unit volume. And yeah, this basically straight follows from the Lorentz force for a single particle. So instead of single particle, we now have, you know, for a volume element. So all of that is pretty straightforward. Okay, so let's come to the type 2 problems. So type 2 problems are solved when you say that I know what rho and J are. So I know what the charges are doing. I know their density, I know their velocities. So which means I can calculate rho, which is the charge density. I can calculate J, which is the current density. Now, how do I get to the fields from my knowledge of where the charges are and what they are doing? And you basically use the 4 Maxwell's equations to do that. I'm sure you're all familiar with Maxwell's equations, but we can do a quick recap. The first equation is divergence of the electric field is equal to 4 pi times the charge density. And again, just to recap, divergence is basically a measure of, if you have a vector field, then divergence is a measure of how much of the vector field is emanating from a given point. So I like to think of this in terms of traffic. So if you think of traffic flowing on a highway as a vector field, so it has some magnitude. So that's the density of cars on a highway, and it has a direction. It's the direction in which the cars are moving. And the divergence is basically a measure of how much traffic is emanating from a given point. And it has this nice intuition of it being equal to the charge density, because you might remember from your electrostatics that if you have a point charge, then the electric field is basically radially emanating from that point charge. So if you increase the charge, then you have more density of lines of force which are radially coming out of that point. And this is basically saying that mathematically, it's just saying that the divergence, which is the amount of vector field which is emanating from a point, is equal to the charge density in that point. So that's Gauss's law of electrostatics. There's a Gauss's law of magnetostatics, which is divergence of B is 0. And this is again a statement that's analogous to the first equation we have, except we have 0 here, and it's basically telling you that there are no magnetic monopoles. So magnetic field is special, or at least different from the electric field, in that you can have an electric field radiating out from a point, but you can't have a magnetic field radiating out from a point, because just like we have positive and negative electric charges, we don't have magnetic charges. There is no magnetic monopole, at least in our current understanding of physics. So this one is straightforward in terms of the intuition. You can never have a magnetic field that's always emanating from a point, because there's no magnetic charge that exists in nature. The other two laws are basically Faraday's law and Ampere's law. So Faraday's law explicitly relates the electric and the magnetic field, and so does Ampere's law. So let's go one by one. So this is the curl. So curl of the electric field, and again, the way to think about curl is a measure of rotation, right? So just think of a roundabout or a traffic circle where the cars are going around. That is kind of an intuition for what curl is. Curl measures the amount of rotation that is there in a vector field about a given point. So if you think of the center of the roundabout as the point, then the amount of curl around that point is basically some kind of a density of cars that are moving around that point. So this basically tells you that a circulating electric field, so something that has curl, generates a time variable magnetic field. And that is basically Faraday's law. Again, so the last one is Ampere's law. Actually, this might be a little bit of a misnomer, because Ampere's law was missing this term here, which I call the displacement current here. So in its original form, Ampere's law was curl of B is 4 pi by C times the current density. And what that's again telling you is the curl of the magnetic field. So the amount of rotation in the magnetic field is basically proportional to the current density. And again, you have this intuition from magnetostatics, where you might have calculated what is the magnetic field of a wire that is carrying current, right? And so you have some current density J. And so let's say you have an infinitely long wire. This equation is basically telling you that J gives rise to a circulating magnetic field. So you know the right-hand rule, where if the wire is along my thumb, then the magnetic field basically curls along the wire. And that curving of the magnetic field is basically the curl here. So that was Ampere's law, but Maxwell basically, almost in an ad hoc fashion, added this term. And the reason he did that was to make these two equations symmetric with respect to the electric and the magnetic field. And you'll see that you actually need this term to get an electromagnetic wave. And the reason for that is an electromagnetic wave is basically an electric field generating a magnetic field, which generates an electric field, which generates a magnetic field, and then the wave propagates. And so you need some kind of a symmetry between E and B, and this term basically completes that symmetry. And so it's usually called the displacement current, and that was added to Ampere's law by Maxwell. And you'll see soon that this term, the presence of this term actually leads to electromagnetic waves. Okay, so here are also the integral forms of all the Maxwell's equations. And so the ones which we saw here were the differential forms. So all of these vector operators, the divergence, the curl, these are all differential operators, right? I mean, it's just a derivative operating on a vector. That's what it is. So you can also write the integral form of these equations. So divergence of E is 4 pi rho, and here's the integral form. And just notice here what the meaning of the signs of the integrals are. So if a double integral means it's a surface integral over on two dimensions. And when I put a circle here, it means it's on a closed surface. Okay, so this is basically trying to measure the amount of electric field that is emanating from a point. And so what the integral form tells you is that, well, if I imagine a closed surface and I integrate the electric field along the closed on top of the closed surface. So imagine a sphere, and I'm just doing the integral on the surface of the sphere. It just has to be a closed surface. It doesn't have to be a sphere. It can be a cube, whatever. It's just a closed surface. That is going to be equal to the total amount of charge enclosed by that surface. So this is the volume integral. So that's the volume inside the closed surface, and that's the total amount of charge inside that volume. Okay, so this actually, let's go to this equation here first. So this is exactly the same as Gauss's law, but for magnetic fields, and the right-hand side is 0. Everything else remains the same. Okay, so this one is Faraday's law. So this is the curl of E is minus 1 over C dV by dt. And you can integrate this out, and this is the integral form of that law. And so just like we did a closed surface in Gauss's theorem, in this case, we're going to do basically a 2D surface. Okay, it doesn't have to be a closed surface. It just has to be a surface. So you can just think of it as a disk, which is just a 2D surface. Again, it doesn't have to be a disk. It can be any arbitrary form. And the left-hand side is basically a contour integral, which encloses that 2D surface. Okay, so if you imagine a disk, it's the perimeter of the disk. So you need to do this integral over the perimeter of the disk, and delta S here is that surface volume element. So disk in the case I'm talking about. And on the right-hand side is basically a 2D integral. And you can kind of recognize that this is measuring the flux through that surface, right? So ds is basically normal to the surface. B dot ds is the component of B that is normal to the surface, and you're integrating that over the surface. So this is basically a measurement of magnetic flux that is going through that surface, and the time derivative of that. So the rate of change of magnetic flux is what you have on the right-hand side, and that is equal to the contour, the closed contour integral of the electric field along the perimeter that bounds the surface. Okay, something very similar in Ampere's law. I mean, the intuition is the same. You have a curl on one side and d by dt on this side. The intuition is exactly the same. And so I don't think this requires further explanation. You again have an integral on a closed perimeter that bounds the surface. And then you have a measurement of surface flux in this case. There must be a vector sign here, sorry, over ds. ds is a vectored quantity. Okay, so those are Maxwell's equations, and we also spoke about the Lorentz force. So at least in a basic formulation, how do you solve problems in electromagnetics? You'll either be using the Lorentz force law or Maxwell's equations to get to these solutions. And yeah, that's the most fundamental formulation we have.